I'm Soraya Faruqi, and I'm the Director of Communications at the university's Space Research Association, which is sponsoring the press conference. And I'm here assisting Julie Tigleski, who is a communications manager at Lunar and Planetary Institute. So I just want to give you a couple of housekeeping items. The DART Media Kit will be live at 12 noon at the LPSC website and on the press page event. So all images, all the information that you need, the press conference, the press releases, and other pictures, etc., will be available there. For the format of the conference, what I will do is I will introduce the moderator, and the moderator in turn will introduce the other members of the panel. We will be taking 2 questions from the folks in person, and then 2 questions we will be taking online. Julie will be moderating the questions online, and I think Paul Abel is probably going to be taking the questions for those of you who are in the room. And so welcome once again to this press conference, the very first one of this week. And I'd like to introduce Mike Buckley, who is the Senior Communications Manager at Johns Hopkins Applied Physics Lab. Thank you. Mike, take it away.
All right, thank you. This is really exciting to be here. You know, it was just about 6 months ago, on September 26th, that NASA's DART spacecraft intentionally and accurately collided with the asteroid Didymos. It was marking humankind's first demonstration of a planetary defense method known as asteroid deflection. Now, since then, the DART team at the Johns Hopkins Applied Physics Laboratory and institutions around the world have been digging into this data. They continue to look at this, and they're analyzing the data, not just from the DART spacecraft, and its ride-along CubeSat, LICIACube, from the Italian Space Agency, but from observatories like the Hubble Space Telescope. And members of the DART team are here today to talk about this latest results. So I'll introduce them. This is Nancy Chabot. She is the DART coordination lead from the Johns Hopkins Applied Physics Laboratory. Carolyn Ernst, the instrument scientist for the Draco imager, also from the Johns Hopkins Applied Physics Laboratory. Maurizio Paola, he is on the LICIACube science team, the Italian National Institute for Astrophysics. Angela Stickel, DART Impact Working Group lead from the Johns Hopkins Applied Physics Laboratory. And Jianyang Li, DART investigation team member from the Planetary Science Institute. Now, they each have their statements first, but before we even begin that, we'll take a look back at the accomplishments of the DART mission.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss. 4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
I think you could see us all celebrating every time we see that still. It's, it's been 6 months, and yet somehow every time it brings back the moment of what an accomplishment that was for the whole team. Years of development to hit a small asteroid in space that had never been seen before when it's 7 million miles away at 14,000 miles per hour. That was a major accomplishment. But since then, we've also been really busy. There's been 6 months, and we've had to figure out how much we deflected the asteroid, what are the main results. And we're happy to be here today in order to share some of those new results from the team. Before then, it's always really important to say up front that this has been a huge team effort. You saw the Draco images there. We're going to hear more about LICIACube that captured and witnessed the event. Telescopes on all 7 continents and in space have contributed to DART's campaign that we've had so far over these 6 months going on. And we have a team of scientists on the investigation team that are from more than 100 institutes representing 28 different countries. And that's all come together here today. So you see the 5 of us up here, but really there's a much deeper team than that. And it's just a joy to be sharing these results at 6 months out. My only role here is to briefly sort of summarize and set the stage for everybody else who will present those. And that's just to walk through exactly what happened with the DART experiment. So we knew ahead of time that Dimorphos goes around Didymos every 11 hours and 55 minutes. Ground-based telescopes had characterized this extremely exactly from looking at it over decades. And so the DART spacecraft came screaming in at 14,000 miles per hour. LICIACube was kicked off 15 days in advance, captured spectacular images, and saw the ejecta that resulted from there. And that nudge changed the orbital period of Dimorphos around Didymos. And we've measured that now by 33 minutes. If the DART spacecraft had just slammed into Dimorphos, and that is the only momentum that had been transferred, it would have been about 7 minutes. And so 33 minutes is much bigger than 7 minutes, with showing that this is a very effective way to deflect an asteroid. It's an efficient technique. On March 1st, these first results were published in Nature, sort of detailing that this was a successful impact for the first time to transfer the orbits in space, the trajectory, that it was changed by 33 minutes, that what Hubble saw for the first few weeks afterwards with all of the ejecta, and as well that this was a very efficient momentum enhancement factor that you got from all of that ejecta. But now we're digging into this because we don't want to know just what we did to Dimorphos, but we want to understand what that means for potentially applying it in the future. And so you have to dig it into the models, get into the models, understand that kinetic impact event and what it means. And along with that, we're still actually getting data. So a lot of times you see that movie, people think things are over, but the telescopes honestly have been very busy for the last 6 months, and observations are still continuing even now. This is from just February 21st, so a few weeks ago. 147 days post-impact is what you're looking at here. And you can see there's still a very clear ejecta tail there coming off of the Didymos-Dimorphos system. And these observations with ground-based telescopes are going to continue through the end of March. Hubble is going to go even more than that, and John Young will talk a little bit about that. But there's going to be a lot more to come from this project, and I'm going to pass it over to Carolyn to talk about some of the specifics with the DART impact and the impact site.
All right, thank you. I want to start by kind of reintroducing us all to Dimorphos. This is a new image mosaic where we took the final 10 full-frame images of Draco. We overlaid them with the highest resolution on the top, and it gives us our clearest view yet of the whole body, but details towards the center there. Dimorphos is about 175 meters across, and we know everything we know about Dimorphos and how it looks because of the Draco imager. So Draco took an image every second for the final 4 hours of the mission before impact. The final hour or so of those images were live streamed on NASA TV. And again, the final 10 were put together here to make this new image. I'm happy to say that the in-flight data from the DART spacecraft are now all available at NASA's Planetary Data System. So anybody in the community and with the public can go and look through all of the over 259,000 Draco images that were taken in flight. You can pick your favorite one, and you can explore this data set like we have been for the past 6 months. You'll see Dimorphos in various different orientations wherever you look in publications and with the press. And this one here is shown with Dimorphos's North Pole up. And I like to remember what the correct orientation is because I feel like it looks like a happy fish swimming to the left. with its nose kind of pointed up. And so from now on, you will not be able to unsee the fish, and you will know where the North Pole of Dimorphos is. We have named 5 features on the body. These names were proposed to the International Astronomical Union. They have a naming theme of percussion musical instruments, and the IAU accepted these names. These are all for boulders or saxum, and I'm going to show them here. This really helps us to communicate from publication to publication or with the public about what we're talking about, so we're consistent. We have 3 boulders towards the center there, Atabake saxum, Bowron saxum, and Kakavela saxum. You can remember those because they're also A, B, C. The nose of the fish is Dol saxum, that's a big boulder off on the limb. And then there's a tiny rock that is used to define the coordinate system, the latitude, longitude of Dimorphos, called Punio saxum. We learned and were reminded by Nancy that we know a lot about what happened. We know we produced a lot of ejecta. We know we made a 33-minute change in the orbital period of Dimorphos about Didymos. And we have measured the momentum enhancement factor, and these are all critical measurements for the DART mission, but those alone are not enough to understand the DART impact in the broader context of planetary defense and how we might apply a kinetic impactor technique towards a different hazard. So again, we have our global view of Dimorphos on the left, and we have the final full Draco image blown up here on the right. You can see the footprint of that image on the body. And the first thing to note is the impact site, like the body as a whole, is really covered in boulders. It looks a lot like the other small near-Earth asteroids we've seen up close with spacecraft, Itokawa, Bennu, and Ryugu. And that suggests that the whole thing is kind of a rubble pile structure, so a collection of boulders and rocks and pebbles kind of pulled together by its own gravity. We have located the impact site. You can see that represented by a circle in the full frame image on the right. And we know that site to within 66 centimeters, which is smaller than the size of the spacecraft bus. The surface is full of unconsolidated material that's going to be easy to mobilize. So expect to see a lot of ejecta, which indeed we did. The spacecraft bus would have hit kind of within this nest of boulders into kind of generic Dimorphos matrix here. But the solar arrays were quite large. They extended across, away from the spacecraft bus in this image, kind of up and down. And we suspect that they would have interacted with Atabake saxum at the bottom and Bowron saxum at the top. And so it's important for us to reconstruct the impact and the orientation of the spacecraft to understand what hit what and when. So I have 2 looping movies here that show the spacecraft impacting into a digital terrain model of Dimorphos. And you can see here that the spacecraft bus does indeed hit kind of within that nest of boulders, but the 2 solar arrays indeed do interact with Atabake saxum, which can be seen in the foreground there, and Bowron saxum. Both of those boulders are about 6 or so meters across and about 2 meters high. If you look at a finer time than these videos are showing, we actually find that both panels and the spacecraft bus hit the surface at almost the same time, within microseconds of one another. And that means that there would have been no shock communication across the spacecraft. In other words, if the solar panel hit, the bus would not have noticed. The bus hit, the solar panel would not have noticed. I'm going to zoom in on the view on the right there because we really want to take a closer look at what was happening with the spacecraft bus. And before I leave this, I wanted to note that we think that the panel that hit Atabake hit more edge on, and the panel that hit Bowron hit more face on. So here's a zoom in of a detailed rendering of the spacecraft with everything positioned as it was at the time of impact, just before it hit the surface. What you can see is that the bottom surface of the spacecraft bus, which is about 1.2 meters across, it's not a flat cube, right? It's not a flat face. There's components of the spacecraft that are hanging off of it. And if you take a closer look at the center in that cylinder is where the Draco imager was, but the thing sticking off to the left side there is the star tracker. And we think that the star tracker was probably the very first piece of the bus that hit the surface there. And so we know that this is a complicated system. We have a very blocky target. We have a good initial understanding of what happened, and it's important to take that into consideration when we're talking about interpreting things that we've seen from ejecta images to impact simulations. And so now I'm going to pass it off to Maurizio to talk a little bit about what LICIACube saw.
Thanks, Caroline. So my name is Maurizio Paiola, and I'm describing a little bit more in detail the LICIACube spacecraft itself. LICIACube stands for Light Italian CubeSat for Imaging of Asteroids, and it's a 6U CubeSat that was brought by DART, and 15 days before the impact, it was released. In an automatic way, it was following the target, and then, of course, performing a closest approach around 55 kilometers from Didymos and Dimorphos itself. It's a project that was managed by the Italian Space Agency, and it was developed by Argotec in Turin. And of course, the PI is Elisabetta Dotto from the National Institute for Astrophysics. And inside the team, there is also Politecnico di Milano, INAF, University of Bologna, and also CNR IFAC. So LICIACube is characterized by two main cameras. One is called LIA, which is an narrow angle camera. It's a panchromatic one. And then there is LIUC. LIUC is an RGB camera with a little bit smaller spatial scale. Let's say it's a wide angle camera. And again, it's a 6U CubeSat. And as you can see it here, it's a very small one. And it's really impressive to believe that all this technological development is really inside a box that is a little bit smaller than a shoebox itself. So the main goal of LICIACube was, of course, to observe the impact of DART on the surface of Dimorphos, and also getting images of the ejecta and the development of the ejecta themselves. So as you can see here in this GIF, we have LIA images. And as you can see, let's see if it's working. Okay, yep, it's working itself. So you can really see the flash when DART was impacting the surface. So these kind of images were taken 30 seconds before the impact itself, up to 30 seconds after. So in 1 minute, we were really seeing the flash and the ejecta development. But really one of the highest spatial scale images that we had, it's really this one, which is an impressive one. Of course, this is an image that was oversaturated in order to see all the tiny little details of the ejecta themselves. So you don't really see the surface of Dimorphos, and you don't really see the surface of Didymos itself. But we also have, as I will show you later, another set of images, really high resolution. And as you can see here, from a scientific perspective, it's really a treasure trove. I mean, we were kind of expecting something that was symmetrical, but in reality, it was totally something different. We can really see that there are these kind of filaments, boulders ejected from the surface, and different kind of densities on the ejecta themselves. But of course, LICIACube is not just the ejecta, it's also observing the surface. And as you can see here on the left-hand side, we have images taken at a distance of 72 kilometers before closest approach. Remember, closest approach occurred 3 minutes after the impact of DART at a distance of 55 kilometers. So on the left-hand side, images at a distance of 72 kilometers, you can really see like boulders on the surface, craters, and also other tiny little differences and surface properties of Didymos. And of course, on the right-hand side, you can really see the unaltered surface of Dimorphos, and maybe there is, we are studying it, maybe there is kind of a difference in composition. And on the right-hand side, this is an image that was taken 71 kilometers after closest approach. And again, I was talking that the main goal is the ejecta, and once you zoom in on the RGB images of LIUC itself, you can really see that there is a globally inhomogeneous and uncollimated dust distribution. On the right-hand side, you can also see this kind of aperture cone that we developed thanks to the DART impact, and it's a well-defined dust structures also in Dimorphos proximity. And with this one, I'm leaving the floor to Angela.
Thank you. So now I'm going to shift a bit to, we have these beautiful images, these wonderful observations. And you know what Nancy said at the beginning was one of our jobs now is to really understand, what are they telling us? What can we learn about Dimorphos? What can we learn about our models and how we can apply the knowledge from DART to future planetary defense simulations and understanding should we ever have to do this for real, right? So one of the things that we've done is we took this beautiful image of Dimorphos and we wanted to simulate DART the best that we could. So we can take things like the shape model and the boulders that we see on the surface, and we can create a simulated Dimorphos. And so what the team has been doing is we created this simulated rubble pile-like asteroid that looks like Dimorphos. You can see the little fish's nose there. And we filled it with boulders to mimic the asteroid as we understand it. And then we want to impact into this simulated Dimorphos and do it as faithfully as we can. So you can look here as a close-up of the impact site with a rendering of the DART spacecraft on top of it. So this is similar to one of the images that Carolyn showed. We placed these two large boulders here to represent Atabake and Bauron, and we impact kind of right in the middle of them, like Carolyn showed, and have representations of the solar panels hitting both of those boulders. And we can use this and we can vary things about the asteroid, right? One of the things that we want to know about Dimorphos is really to understand, how does the material behave when the spacecraft crashes into it? Is it very strong like a rock? Is it very weak like sand? We can try to understand the interior of Dimorphos using simulations like this. And so we vary a lot of those properties. And they tell us a lot about what Dimorphos might be made of, how that material moves and interacts. And we can use all of the observations that were done using Draco, LICIACube, and the space telescopes, and try to match that with our simulations. And so I'm just going to show one example where we kind of tried to put all of this together and see, what can we match right now, and what does that tell us, and what might we still be working on. So I'm going to show an impact simulation into this Dimorphos hitting at this impact point, and show you what some of these results look like. So we've got this nice animation here of a simulation that was performed by one of our team members, and you can see there's kind of a lot going on here. And so we impacted at the impact site, and this is a couple of seconds after the impact. And you can see that we have developed this beautiful ejecta curtain. You see things that look reminiscent of what was seen in the LICIACube images, right? We see this wide ejecta cone. We see these kind of ray-like structures. And all of that is because we hit into this rubbly surface. So, Dimorphos is not a smooth, flat object. We have all of these boulders, and they really change what happens to the material. We get these sort of concentrations of ejecta coming out in sort of preferred places because of those boulders. And it makes that ejecta curtain wider and much more complex. So that's one of the key results that we're finding, is that these boulder surfaces, we know it has a big effect, and we know that that is one of the things that contributed to what we saw with DART. We are looking at a lot of these simulations and using things like these kinds of images to match what was seen. And what we're finding is that if you do that, we can start making some predictions for what Hera might see when it gets there. And one of the questions we get a lot is, how big of a crater did DART make? Right? This is a really important question, because it's one of the things that can best constrain our models. It's one of the most visible things, following an impact. And we think that, when we do sort of reasonable material properties, things that can match the observations, that DART created a crater between about 40 to 60 meters big. So it's big. Dimorphos is only 170 meters in diameter. Kind of look at the long end. And so this puts a big crater on the surface, and it's something that we can look at and test with Hera. This is something, this is an artificial crater, but is a very, you can think of objects throughout the solar system that have these large craters. It's kind of common to see them naturally. And so it'll be really exciting to see it, an artificial one, in a few years, hopefully, when Hera gets there. So that's what happened directly right after the impact. And then Zhanyang is gonna talk a bit more about what we've seen since.
Thank you. Okay, my name is Jianyang Li, and I'm from Planetary Science Institute. And now you have seen the details at the impact site and also the closing observations of the ejecta. I'm going to switch it a little bit and back up and zoom out and see what I'll tell you about what the ejecta and what the tail from the impact tell us in terms of our study of active asteroids. So I'm putting up a graph to compare the tail of Dimorphos that created by DART with other active asteroids observed before. And these active asteroids, they were asteroids and they were observed to develop tails. And compare these asteroids, active asteroids with DART impact ejecta and the tail, you can see a lot of similarities there. And you can see all the tails are narrow and long. And if we look at the particle size and the particle size distribution, we can also see a lot of similarities between these tails. So in that sense, DART created an active asteroid that with a tail that lasted for months. And but in all the previous active asteroids, we didn't see the start of the tail. This is because no one can predict when the impact happens in asteroids. But for DART, we knew exactly when this was going to happen, and we knew the impact condition a lot better than all the previous active asteroids, natural active asteroids. So DART actually provided us with the first opportunity to study the development of these tails from the beginning, and hopefully until the end. That's why we observe the ejecta evolution from the beginning, and also we're still observing the tail from now for long term. We have been using Hubble to look at the tail since November at a cadence of every 2 to 3 weeks. And we will keep doing that until the tail becomes too faint to be observed, or until Didymos moves too close to the sun. So Hubble cannot look at it. That's going to happen in early July. And I'm going to show you some images that we took in the past few months and see how the tail changed. This image was taken on November 30th. You can see a bright tail there, and the central condensation is Didymos. And then the second image was taken on December 14th, about 2 weeks after the first one. And then the third one was taken in late December 28th. And you can see the tail is becoming fainter. Then this one was taken on January 19th. The tail is becoming even fainter. And the last one, this was taken on March 1st, about 2 weeks ago. And here, the tail is barely seen. So from these images, what you can see is that the tail changes directions, but that's only simply because the changing in the viewing geometry, because both the asteroid and Earth are moving in space. So more importantly, as you just said, as you just seen, the tail is becoming fainter and fainter because the dust in the tail is dissipating and spreading out in space. And also they are moving further away from the sun. And another thing you can see is that Didymos itself is getting fainter and fainter because it's, again, moving away from the Earth. So hopefully we will be able to, we will keep looking at it, and hopefully we will be able to monitor the whole life of the asteroid tail from the beginning to the end for the first time. So with the, that's our long-term observation of DART of the tail from Dimorphos. And I think DART is a remarkable mission, both because it is the first very successful planetary defense test, but it also offers the opportunity to study a lot of details about the binary system in many respects. And also it had helped us to advance our understanding of active asteroids. With that, I will pass the mic back to Mike.
Okay, well, I mean, from the close-ups right at the surface to even LICIACube just beyond, or the Hubble, what an amazing set of images. I mean, just even cool to look at. And I didn't point out at the beginning that all the graphics that we're showing here today are also available on the DART mission website. And that's dart.huapl.edu/gallery. And you'll find all the graphics that we showed today in that collection as well. So now the plan is to go to see if we have any questions first in the room. And then after we go in here, we'll see if we have online. Okay, we'll move to online.
Okay. All right, virtual participants can use the raise hand feature to ask a question. And when it is your turn, you will be prompted to unmute yourself. Please state your name and affiliation first, followed by your question. Are there any questions by the virtual attendees watching on Zoom?
Okay. Oh, we do have questions in the room. Here we go.
I just wanted to know.
Wait for the microphone.
I just wanted to know, I know that you had planned you had certain expectations with this, I guess, collision. However, did you actually, did it exceed your expectations, the actual collision, or were there some surprises there?
We'll let everybody chime in on that one. Technically, everything that we've seen and how effective this technique is within the predictions. There just were a lot of uncertainties, right? So in that sense, it's not like we're seeing something that was totally unexpected, but it is at the high end, and the deflection is really enhanced, right? And that makes it very promising technique going forward. I think we each had our own specific reactions, so maybe we'll go that route. But I think for me, I knew the final images were going to be spectacular, and somehow they still managed to exceed my expectations. The moment when it came in is extremely memorable, and the fact that NASA was able to share that with the world on the broadcast meant a lot. And then I think I've been really taken by just how spectacular the ground-based and Hubble images have been of the ejecta, and how long that's continued for months and months afterwards, and just what a rich data set that was. Deflecting the asteroid, how much you moved it, how much you deflected it was always the main goal of DART, but we're learning so much from this ejecta, and that's just really a bonus.
Yeah, I want to follow on from Nancy. Just seeing something for the first time is just so exciting. And so you can have expectations and it will never quite be the same. I was surprised by the bulk shape of Dimorphos. I don't think anybody ahead of time thought that it would kind of have an oblate shape. I think people were thinking it would be more like an egg, if anything, and more irregular, because of a lot of the other small bodies we've seen have very irregular shapes, and this one was so regular. So that surprised me, and I was really happy to see it become an active asteroid. So I won't talk more about that because that's Jean Yang's department, but that was really exciting for me.
Yeah, in my case, especially with the LICIACube images, what was amazing is to see all these tiny little details and having something that is definitely not a symmetrical, kind of cone. And this was really impressive, especially because it was really one of the first time that it was used tiny little small CubeSat to get all these details. So it was really something crazy. Once, with the DART images, they were just coming extremely fast, and it was possible to see all them together, right? While the images of LICIACube, they were coming a few days after, and not all of bulk together, but few images a day. And it was really kind of amazing, something impressive to see all these images and all these tiny little details every day is going on. Yep.
Yeah, I'm going to echo Nancy. I think, what we saw was within our expectations, but for me, like every time I see that video, I still get goosebumps. Like the whole experience was just amazing, that a lot of it sort of exceeded, I knew it would be exciting, but it's just very difficult to process still how exciting this has been. I think, we kind of expected that Dimorphos will probably be sort of rubbly. I did not expect it to look like it looks. I think Carolyn's right. It's nice, round, smooth, like fish shape. And, the amount of these large boulders was sort of surprising to me. I think for me, I'm not sure why, but I expected them to be smaller. I don't know. And then, the images, we expected to get images from LICIACube, but just how beautiful and stunning this ejecta is. And the fact that we had LICIACube there was just so critical for us to be able to understand more about this impact process, right? Because as Nancy said, we measured the period change, and it was always plans to do that using a lot of these other techniques, but really understanding the impact requires us to understand the ejecta. And so for me, that was they're just so beautiful. And that ejecta is just so stunning that's been really lovely.
Yes, so I totally agree with everybody said. And for myself, it has been a lot of surprises, a lot of excitement too. In the beginning, we don't know what the ejecta is going to look like. There will have been a lot of prediction, a lot of simulation work, for prediction to predict what's going to happen, but nobody really knows what's going to happen. And then when we looked at the images from Hubble, we were like, we never expected so many features, fantastic ejecta seen like this. And also, especially, for one part of the ejecta evolution, we see the kind of a spiral feature, the features like kind of rotating around and forming that, like pinwheel feature. And that is very, at the beginning, we didn't know what happened. So we had to spend time to figure out the dynamic process to explain that. And then later on, we see those kind of a streak that overlapped with the like the ejecta, big ejecta, wing-like ejecta feature in the north. And those kind of complex structure is what we never expected. That was really very exciting to see those. And another part is the tail, like Nancy said. We knew that we're going to create a tail. The question is, how much ejecta we were going to eject, and how long the tail is going to last, and how bright it is. And it could be like hours, could be days or weeks. And now we see it actually has been months. And so fantastic tail. And that actually made us, put us in a very good position to using DART to apply what we learned from DART to study other active asteroids. So that's a totally bonus, I think.
Thank you so much. And a follow-up question. So what are your future plans? Another asteroid in the redirection test?
Well, everybody's very excited about Hera. I've heard about that a lot there. So the European Space Agency Hera mission is going to launch next year and then rendezvous with this system in late 2026 and take incredible observations in 2027 and see whether like everything that Angela's predicting and her group's predicting in those models is actually correct or not. How much is the surface messed up? What is the mass of Dimorphos? And that's going to be just amazing. And we're so lucky. It's been a really close international partnership from the start between the DART and the Hera team. There's a very long history there, which we will not go into, but the teams are working very closely together. So everything we're learning from DART is fully informing Hera going forward. And it's just a great international collaboration to make that possible. NASA, has a planetary defense coordination office, and they've got a planetary defense line now. DART was the first mission to run off of that program line. The next one will be the NEO Surveyor mission, which is a dedicated IR-based telescope to find the asteroids. Because one thing we didn't talk a lot about is that, DART has got to be part of a larger planetary defense strategy. This is something you do many years in advance, and you can't do it many years in advance if you don't know where the asteroids are. So finding the asteroids is crucially important. And so that'll be there. And what comes next after that, there's some recommendations in the recent decadal survey. I guess from my perspective, the most important thing is that DART is the start, that we've done this now, and we continue to take those steps, that there's a regular cadence of making progress in this area. Now that humanity has reached this goal of deflecting an asteroid for the first time, it's just a tech demonstration. We're a long way from operational capability. So there's a lot of ways it could go. I'll let other people sort of chime in here on, maybe what they would like to see going forward, sort of beyond Hera and NEO Surveyor for the next things.
Well, my background is experimental impact cratering. So, given infinite resources, I'd love to see more experiments. Given that we have only had the data for 6 months and we have Hera that's going to fill in a lot of the pieces, it's really important for us to get that full picture together so that if we were to ever do another kinetic impactor experiment, we would have the right inputs to get additional data out of the system. So I think that's something important to look at, but we do have a lot of work that we can do without actually sending another spacecraft to crash into an asteroid to expand upon this. We've now ground truthed this method with this impact. And so we can use that piece of truth to extrapolate to experiments, to simulations, to better understand what this technique would do in another situation and to understand more about asteroids of this size.
In my case, I mean, I'm really into boulder size frequency distribution on surfaces of asteroids. And one of the most important things will be really having high resolution images of Hera, of Didymos and Dimorphos. So this will really be an important follow-up in order to study all these different properties and then returning back to all the results that DART and LICIACube got. Yeah.
Yeah, like Carolyn, my background is experimental impacts. And so I would love to see a fleet of darts go out there and impact into lots of different types of asteroids. You know, I showed these images and we're able to recreate, you know, Dimorphos, we think we're able to simulate the DART impact fairly faithfully and learn a lot to try to match DART. And DART is such a crucial, like critical tie point for us to show that our models can accurately represent these things, but it is only one data point. And, you know, we trust in our models and we're learning where they're matching well and where they're not matching well to better understand them so that, you know, in the future we can make better models. But having more like data points is always better. So for me, I would love to see that. I would also just think, you know, the more that we can see more asteroids, the more information we have. So, you know, future missions, both from planetary defense, but also just science missions to asteroids are going to teach us so much about how these asteroids are made up, what their surfaces look like, and all of that would affect a kinetic impactor. And so, you know, continuing our, you know, exploration of asteroids is going to be really important to understand how to move the DART results forward for planetary defense.
Yes, I totally support the idea of more impacts. But for this particular one, you know, we're just starting our analysis of the data. And as Nancy said, as I just talked, we are still keep taking data. We didn't have time to look deep into the data yet because we're, you know, just need to take the data right now when the tail is still there, take as much data as possible to get a complete image, complete picture of the whole the tail, the evolution of the whole of the tail. And then next, of course, we're gonna dive into it and answer a lot of detailed questions about why we saw what we saw. So
thank you so much. Thank you.
All right, I think we have a question online.
Hi, my name is Lisa Grossman. I'm from Science News, and I was wondering what the lessons from DART are for future asteroid deflection attempts in like a real situation where we were actually trying to deflect an asteroid. If this was a dress rehearsal for actual planetary defense, what do we do in the real event?
Yeah, I mean, DART was definitely just the start, but it was a huge accomplishment to autonomously navigate to a small asteroid in space at very high speed when it's millions of miles away from the Earth and hit it in north to the center to impact it so squarely. And a major accomplishment, but also a huge challenge. But you can also see how that has high relevance potentially to planetary defense, where you might have limited observations and information about a target that you were concerned about for the Earth. So that accomplishment in itself, improving that technology, has been really important for DART and is one part of it. And then the second part, I think, is just how effective the kinetic impactor technique has shown to be. This is why we had to get a lot of models had been done on the computers or had been done in small scale and experiments. We needed to do a real world test to see how a real world asteroid of a relevant size for planetary defense. Dimorphos is really sort of a priority size for planetary defense at this 150 meters sort of object. how much would we deflect it? And the fact that you're getting this momentum enhancement factor where the ejecta is doing a significant amount of the work, in fact, more work than even what you're bringing in with the spacecraft, just shows that it's highly efficient, and that's very promising. And how much that'll translate to all the rest of the asteroids is there, but it definitely says that there's a lot of potential, that you don't need to make this problem harder than it is, right? If you can just kind of nudge asteroids by running things into them and do this many years in advance because you have that knowledge, DART has shown that that was highly efficient and effective. And so it's really promising, but there also just does need to be next steps of finding the asteroids so you have that knowledge, because this does rely on the warning time of doing this many years in advance. And so that still remains the priority for planetary defense, is gaining that knowledge of, you need the situational awareness to understand any potential threat and then put yourself in the warning time sort of situations. I'll let Carolyn go ahead and jump in here.
Sure. On paper, we thought the kinetic impactor technique would be something that could be in our tool belt if we ever had to deflect an asteroid. But of course, we haven't done it. And so just doing it is important. It gives us hope, right? There is something that we could do that is proven that it can work, and it's fairly efficient. We're being proactive here. We don't have a threat right now, but if there ever were to be a threat, that's not when you want to start experimenting around, right? You want to have a plan. And so this is really step one in developing that plan, so that if a hazard ever is recognized, you can go to that plan and say, okay, do this now. And that was huge. We had never done it before. And now we know that this is a piece of the puzzle that might work.
I just want to add, I think, one of the things that we're finding is, we didn't have to have an observer spacecraft, but if you ever did this for real, having one is super helpful. Not just to confirm that you did it. I mean, that's very important, right? You want something to confirm you hit, although, your images coming in, Draco did a pretty good job of confirming that we hit the asteroid. But just like, showing the aftermath, showing the ejecta, it gives you a little more confidence in, what happens, and allows you to kind of, for me, I simulate these things, and for me, simulating them, that is just so important. And then, if you had to do this for real, having those images, you could maybe say something like, did we hit it enough? Do we need to do something else? Going forward. And so if you have time to have a carry-on space, like a carry-along CubeSat or something, that would be very helpful in a real scenario.
I think time is the most important piece here. We've shown that the technique is a viable thing to use, but you still have to have enough lead time to build the spacecraft, to launch the spacecraft, to get to the intercept position. And depending on the size of the asteroid, you might need to hit it more or less. And so really finding these things is going to be one of the most important pieces going forward.
All right, make one more sweep of the room and online. All right, so with nothing else, I want to thank the panelists, for those amazing insights into this incredible mission. So again, thank you again. And thank everybody here in the room for attending, and those online. We'll point out again on the screen, you can see the sources of information online to get more on the DART mission. There's both the mission website, the dart.jhuapl.edu, as well as www.nasa.gov/DART. And then, so that'll do it for this one, but we'll be back tomorrow at noon Central Time, hear from the New Horizons mission team about some of the latest discoveries in the outer solar system, from Pluto, the Kuiper Belt, and beyond. So thanks again for joining us, and we'll see you then.
All right, end the session. So maybe they'll look at it.
Yeah, no, thanks. I mean, there's no data.